Good afternoon. My name is Daniele Sacchi, and I will present you shortly a work that we have done together with SMT, that is the vendor of Master. First of all, I would like to apologize because of the delay that was related to some technical problems I had a few minutes ago with the microphone. Okay, let's start. First of all, a disclaimer, because the contents are related to a case study that was performed about NVH, and so the results and the explanation will be limited to the main points in order to protect the NDA we had with the customer that asked to provide these results. What will we see? First of all, I will present you the case study. Then there will be a description of the model that have been used at the beginning of the study, and then the analysis of the first modifications and the first results that have been obtained. Then the further design and a criticism of the preliminary modification criteria. And because of that, deep model refining and the show of the results, and last but not least, the conclusions. So let's come to the case study description. The problem was that a gearbox has been found to be too noisy as installed in production run with high unit variability, so also a production problem. The solution passed through extensive testing, master modeling, and development of design changes, and a lot of significant design changes and modeling results to identify and quantify the manufacturing requirements for the critical dimensions for noise control. As a result, a significant noise reduction was found in the prototypes, and especially an understanding of manufacturing changes that have to be implemented to maintain this solution. A note by the writer is that the gearbox under examination is not that of the case study. This is to protect the customer. So a little deeper about the case study. During the prototype test that was performed on the complete vehicle, people were able to feel, to hear the typical whine noise coming from the speed reducer. So a lot of tests have been performed on the test rig by means of phonometric measurements, and a lot of noise levels emitted were measured. Here on the right, you can see an example of the waterfall on the sound pressure that whose legenda is reported here on the right, where you can usually find the frequency that was omitted and the speed of the gearbox. You can see the orders here clearly signed on the waterfall. What I can tell is that here in the spectrum we can find the medium frequency and here the medium high frequency. More or less here in this area is the band of frequencies for which the human ear has the maximum of sensitivity. So what was perceived is the tonal noise you can reported clearly here in the area indicated with 1, 2, and 3. And the purpose of this work is to reduce or eliminate some of these. So the model has been defined in this way. You can see here a 3D image on the upper side of the slide, while on the right side you can see a section schematic. To solve this problem, the study started from a simple model where the shafts are axisymmetric according to Timoshenko theory, modified for shear. The bearings are coming from the catalogs. You can see here the ball bearings and the cylindrical roller bearings. And the gears have ratios and geometries that are similar to those of the case study in order to have results that can be considered in similarity. The problems that are addressed here have a reference to the fifth gear. That is the gear couple you can see up here. And the procedure that is reported in the follow was carried out in the same way also for the other gears in the gearbox. So we concentrate our attention only for the couple of mesh of the fifth gear with the output gear transmission. On the right, you can see the gear geometries that are referred to the output gears and the gear micro-geometries as for crowning and for envelope corrections. These crowning and corrections were obtained using a single mesh gearing software. So in this case, we are using a software that is Master that is able to solve simultaneously the situation and the mechanical situation of a gearbox, considering the whole system. So the gears and the gear corrections that were defined for the project, the design project, are copied and reported inside the model. And after a first run, we can notice that under the nominal loading condition, the contact pattern is not optimized and the contact pressures remains quite high. So you can see here that the contact is on the right side of the tooth flank, and you can see a high pressure in correspondence of the root of the teeth. The transmission error remains quite good and acceptable. The peak-to-peak value is 2.2 microns. This is microns, not millimeters, of course. Again, some results on the preliminary model. You can see here reported both the velocities on the left side, while on the right side, the accelerations that are measured in correspondence of this bearing for the upper results and this bearing on the secondary shaft for the lower results. Having the possibility to read which are the order for the emissions that are reported in this 3D waterfall would be clearly possible to identify that these peaks reported on the same order cut are coming from the same gear, that is gear mesh, pardon, that is exactly the gear mesh on the output of the gearbox. The values that are calculated in this situation is about 76 millimeters per second and 300 meters per square second for the bearing On the other side, on this bearing, it's 81 and more or less 50 meters per square second that are really high. So the first step that is generally performed or followed to solve this kind of problems, or generally the problems in gearboxes, is to refine the gear mesh micro corrections. So a lot of preliminary DOE analysis were performed in order to see which could be the best solution for the micro correction of the gears of the gear mesh that are reported here, and reported some results referring to crowning and barreling relief, that is the continuous correction on the envelope. Here you can see that there is a solution that is referred to 3 different kind of corrections that minimizes the values for the acceleration of on this bearing. So the 3 solutions were examined deeply, and only one of these 3 was selected to go on with the study. You can see, if you remember the previous results, that the crowning is very similar, while on the envelope side, the correction is completely different and increases a lot. So, what are the preliminary results we can obtain in this way? You can see here a couple of waterfalls that were obtained, measuring the acceleration on this side, on this bearing, and the velocities on this bearing. And you can see that while previously there were 308 meters per square second, now we have more or less 84 meters per square second, so 8g. While about velocities, we pass from 76 down to 21, about 21. These results were judged not satisfactory. The vibratory conditions of the gearbox simulated is still too high. So we have to apply suitable design changes considering the changes at a system level and not only on the gear level. To understand what have been done in the next steps, I would like to report or to repeat some ideas or knowledge that we already have in mind. From the elastic point of view, a very simple gearbox that can be identified with a couple of gearing mesh, an input and an output shaft with the support bearing that you can see reported in 3 dimensions here. We can refer to a schematic section of the gearbox, and we can see that here we have the 2 shafts, the input and the output shaft, that are supported by a couple of bearings each, and there are the gear in mesh. Here it is considered to be the pitch line or the pitch cylinder, as you prefer, and just here is bearing the vibration that is then transmitted to the housing. And I go a little deeper in the description of the way of working of this model. And here you can see that springs and masses have been used, and also some indication of a pulsating force. The pulsating force is generated by the transmission error, that is obtained or that bears during the working of the gears in mesh. And the transmission error here is applied between the two meshing teeth surfaces and depends in value. You can see here an example of transmission error, and depends on the geometry of the teeth, the macro and the micro geometry, the stiffness of the teeth, the load in the mesh. Then this is transferred passing through the spring, the masses, and I didn't report it also the damping that is in parallel with the springs. A note has to be defined about the springs, because at each spring here reported is in reality to be considered as a matrix of stiffness of the gear, for example, of the shaft or the bearings, and the mass has to be considered as the mass matrix of the system. So the irregularities during the meshing generates, as seen, a transmission error that generated forces that are transmitted by means of the gear. And these forces that you can see here about the transmission error depends on the position inside the pitch line. And they are repeating exactly with the number of the teeth or the pitches that are in the gear. So if n is the shaft rotation and z are the teeth, the number of teeth or pitches, this means that the main meshing frequency, so the first meshing frequency, is z times n. If you measure the acceleration of the velocities with a proper accelerometer, you can see that many other Fourier frequencies are also present because of the design of the tooth flank errors, teeth deflections, and microgeometry. The irregularities on the transmission error are so transmitted to the shaft, and these are transmitted to the shaft depending on the dynamics of the gear, in order of the dynamic that is derived by its stiffness and geometry on the gear web. The shaft then receives the forces from the gear and transmit them by means of its dynamics or transfer function to the place on the shaft in which the bearing is reported. So the shaft is transducing the forces coming from the gears to the bearings, and the bearings themselves, depending upon their dynamics, their inner dynamics, are able to transmit the loads received from the gear passing through the shaft to the housings. The kind of what is a transmission function of the bearing depends on the model of the bearings that we are considering. We know that the oil film bearings have a very high damping characteristics, or depending on the fact that they are rolling bearings. Depending on the bearing position, because of the inner equilibrium inside the bearing, and the configuration that the bearing has during the mesh. The housing then vibrates, and its surface excites the surrounding air, so generating the sound that we perceive with the ears, the so-called airborne noise. The housings have generally a very large dynamics, and are able to vibrate in a very large band of the spectrum. This means that the surface of the housing is able to excite the surrounding air in a very large spectrum of emissions, with amplitudes and intensities of pressure fields around that depends on the housing surface spectrum in excitations, by the physical status of the air, depending on the mist, for example, and the situation all around the emitting housing, that is the ambient all around the housing of the gearbox. For example, objects or walls that are all around the housing that are disturbing the acoustic field so generated, so that in the real cases, the free field acoustic emission is never reachable. We are at each time working with the reverberated or confined acoustic field. So the main changes, taking into account the complete system model that have been done further, are involving the bearings in combination with the defined gears. The first attempt was done introducing tapered roller bearings in the input shaft, in the secondary shaft. You remember that here there was a ball bearing and here a cylindrical roller. With a configuration like that, we obtained we reduced by a value of more or less 10 the peak value of the amplitude of the speed down to 6.9 millimeters per second. I remember that at the start it was 76 millimeters per second. So what has been obtained in matters of velocity and acceleration are the two diagrams that I reported here in 3 dimensions, where you can see the first order cut for the speed and acceleration, and also the second order cut. What is missing here seems to be a higher order or higher frequencies in the response of the gearbox to the gear meshing we have here, considering the fifth gear in that is driving. And so to understand what I am saying, I prefer to refer to a Campbell diagram of the gearbox, in which here in the x-axis reported the power input speed in revolution per minute, and here the frequencies. In horizontal dark gray are reported the lines that are referred to the modes of the gearbox. You can see that there are a lot of modes, and here all these color line are the order of the harmonics. Here in the lower side of the Campbell diagram are reported the first order harmonics, while on this area are reported the higher order harmonics of the gear meshing, both of the fifth gear and the output gears. And what we can see is that all these harmonics should be able to excite some of these modes. So it seems to be strange, analyzing the results at the previous slide, that there is no order reported as a result. So it was better to review the initial conditions of the problem. And analyzing the initial waterfall that I reported, we can see that there are, yes, some orders that are exciting in a bad way the sound all around the gearbox, but there is also another order here that has a peak that is well around the 4,000 hertz. That is more or less the maximum sensitivity area for the human ear. So we need to refine deeper the model we have used. And the choice has gone in a direction to change the dynamics of the output shaft. Here we have the differential that, if you remember, was modelized as a simple shaft, a Timoshenko shaft. While in this case, we prefer to have a FEM description of the housing and the output shafts, and also we want to introduce the straight bevel gears that are inside the differential, and also the cross support of the bevel gears that are inside the differential. In this way, increasing the dynamic level of the last shaft, we obtained a waterfall diagram that is much more significative of the behavior of the gearbox we are analyzing. We can see here the first order cut that are referred to the output gearing mesh, while on the central part of the waterfall that just before was reporting nothing, we can see that there are some peaks that are also putting in shadow the high peaks we were able to measure referred to the output gears. Here we are reaching more or less 30 millimeters per second instead of the 20 millimeters per second of the previous analysis. And you can see that there are also a lot of different harmonics at higher frequencies. So having in mind these results, we have further introduced in the model a lot of different modifications in order of optimal microgeometry of the teeth, preloaded taper roller bearing on the secondary shaft, and bearing preload on the differential housings. What we have seen is that all these modifications are reducing the values of the emissions in the first order cut that is referred to the output, to the only output gear, while only acting in this way, all the orders related to the harmonics excited by the fifth gear are remaining really evident. So this forced us to introduce a lot of different modifications, starting by the way that the gearbox is responding to the harmonic excitation given by the fifth gear. And here, considering, for example, one of the peaks in emission that was measured on the bearing, I reported the printout of the auto-vector, let me say, so the deformed shape due to the response to the fifth gear harmonics excitation. And we can see that the first shaft is has a very low stiffness, that the right side of the shaft is deforming and exciting a lot the output gears. You can see that the output gear is exactly in this direction, and that also the secondary shaft is deforming a lot, and this is because the gears are have a quite high masses. So it is necessary to increase or to design in a better way the geometries of the shaft to make them a little bit stiffer and lighter. Another point that you cannot see here is that here where you can see the fifth gear in mesh, the body of the wheel of the fifth gear is being excited in counter phase, as referring to the secondary shaft. So all these thoughts have been reported in order to reduce the emissions by the gearbox, and starting from the bearings that are a good starting point to stiffen the shaft. A proper preload has been defined by means of a DOE analysis that considers contemporarily what are the effects on the bearing life of the bearing life, the four bearing life that you can see here, applying the preload, the proper preload. The preload of the primary shaft is reported here, the preload of the secondary shaft is reported here, and here you can see all the different spider connection that that the different preload have with the selected bearing life. So after having defined the bearing preloads, after having defined the geometries of the shaft and defined the bearings on the input shaft and the secondary shaft, the micro-geometries of the gears, and after having modified the design of the gear bodies on the secondary shaft, these results were obtained. And to ease the comparison between the previous one and the last one, I reported them inside a 3D waterfall having the same maximum value in the axis. You can see that here there were, in this area, there were all the harmonics of the fifth gear, while here they are practically completely eliminated. The harmonics on the first order cut, that is related to the orders excited by the output gear in mesh, are very, very low, while there are a couple of peaks here that are less. Here we are working with less than 10 millimeters per second, while this peak is in the range of the engine that is close to 7,000 RPM, in which the engine is not used. So at the end, this kind of results were considered at least preliminarily acceptable. To obtain these results, I'd like to show you which are the main modifications that have been introduced. In order of bearing modification, you can see here on the left side of the slide the situation of the gearbox as it was designed at the beginning of this job, and on the right side you can see the design of the gearbox as it is at the end of this job. So the bearings on the input and the output on the first shaft and the secondary shaft have been changed with taper roller bearings with the proper preload calculated as seen before. And also on the differential shaft, a preload has been introduced. The shaft design has been changed in order to increase the external diameter and reduce the weight on the extreme parts, the two ends of the shaft, to the right and the left, in order to reduce the effect that was given by the strong deformation that was measured here in the harmonic response we analyzed before. Also, the output shaft had been changed in a matter of geometries, increasing the diameter and so changing also the diameter and so the stiffness of the bearings that are reported just below the gear's body. Another change is due to the reduction of the masses, what I already said, described in the previous slide, but you can see that also there is a different selector here for the synchronizer. All the gear bodies on the secondary shaft has been changed in order to reduce as much as possible their masses and to increase the stiffness of their connection with the output shaft. Also, the gear micro-geometries has been changed in all the gears, and if you consider that generally a lot of people are referring to only modifying the gear mesh, you can see that this is only one part or only one action between a lot of others to reach a proper result. Fundamental in this study was the proper description of the behavior, the dynamic behavior of the differential introducing the FEM of on the housings. So as a conclusion, we can say that modifying only gear teeth was generally not sufficient to solve NVH problems. And in addition, we have seen that a systemic approach is more suitable for solving this kind of problems. And it should be added now that the model analysis alone is not generally exhaustive to understand such problems. It's much better an approach that is passing through the systematic study of the harmonic responses of the complete system to the significant excitation inside the gearbox. This also means, as a conclusion, that the design of the complete gearbox should be drawn having clear in mind that one of the main targets is NVH. And so the gearbox must be designed with a different approach, with having only the strength in mind. The dynamics and the NVH of a gearbox must be considered since the beginning of each gearbox design, and it is possible with the software that are now on the market. The last conclusion is the comparison of, so that means that this work is working similarity with the case study. You can see the first array waterfall that we have seen and the results obtained. And here we can see in the same frequencies here and here, the starting of the gearbox reported in this waterfall, and here the optimized waterfall that is reported and obtained all along the study. Here a typical indication reporting the torque here in the x-axis, and here the peak-to-peak transmission error of the original design and the optimized gear that has been obtained for the output gears in this study. So I have finished. If you have any question, this should be the moment. Otherwise, you can please mail me at this email address. Many thanks and have a nice afternoon.